the magnetic fields are just like electric fields, right? But it's a different kind. And the source for magnetic fields are the charges in motion. Remember, for electric fields, the only required thing is to produce an electric field is a charge particle. And charge particles, the main source for the charge particles are electrons and protons. And we can easily produce free charges by rubbing some materials to each other and get rid of some electrons or acquire some extra electrons, and this will produce electric field. But for magnetic fields, again, if you ask the definition of magnetic field, whatever the kind of field is, magnetic or electric, we define the field in terms of its force. Okay. If there is no force, you cannot talk about any field. Oluyor. The charges in motion, whether it's constant velocity or non-constant, will produce magnetic fields. I will discuss this later. But the charges must be in motion anyway. So we define the magnetic field by just the effect of the magnetic field on the charge particle which is in motion. If you have any charge particle and if you move this charge particle inside the region of space where there is a non-zero magnetic field, then you will feel a force on the particle. This force is a very special force which is produced by a magnetic field, and it is always perpendicular to the instantaneous velocity. If the particle goes in this way, the magnetic field will be always perpendicular this way or this way, depending on the charge, whether it's minus or plus. You see on this picture, if it's a plus charge, if it's moving on the upward direction, and if the magnetic field is in this direction, which is perpendicular to the plane of the motion, then the force will be in this direction. As you see, the charge velocity, the magnetic field vector, and the magnetic field, they're all perpendicular to each other. There are three vectors, the velocity vector, the force vector, and the magnetic field. They are all perpendicular to each other, and they form a right-handed system. Do you know what right-handed system is? So the right-handed system means if you have three perpendicular vectors, right, and any one of these three perpendicular vectors can be expressed as the cross product of the other two vectors. Okay? For example, in here, the magnetic force is just the cross product of the velocity vector with the magnetic field vector. And this is determined by the right-hand rule. If you show your four fingers in the direction of magnetic field, V cross P, we will find the V cross P. If the four fingers shows the direction of magnetic field, and your palm facing the velocity vector, then the force vector is this. If this is velocity vector, if this is magnetic field, just facing the velocity vector, the magnetic field is the direction of your thumb. So you can read about this in your text, and it's not very complicated to understand this right-hand rule. And in terms of the unit vectors, I cross J is K, J cross K is I, and K cross I is J. So it goes around this counterclockwise circle. And if you go in the other around, in the clockwise direction, all the products will be minus. So as I said, the source for the magnetic field are the charges in motion. That means if you have a current, then there will be a non-zero electric field, non-zero magnetic field around this current. And this, you see, this is a wire, the orange, and the current flow of this direction. The current direction is your thumb, and your forefinger gives the direction of the magnetic field produced by this current. Okay, so the magnetic field around this current is always circles, and the magnetic field never crosses anywhere in space. But we know that the electric field crosses at one point, at some points in space, and these crossing points are nothing but the charges. As long as you have electrostatic charges, the electric field vector will cross, will emerge from that point, or it will end on that point. If the charge is minus, if the charge is plus, the field vectors will emerge from the point charges. So as I said, both fields are producing some force effects on charged particles, but there are also unique properties that differentiate between these two vector fields. As I said, the electric field vectors are crossing at some point in electrostatic, but magnetic field vectors never cross. They all complete loops, okay? Whether they are perfect circles or they may not be perfect circles, they may be an irregular shape, but they always will be a loop, okay? They will always loop and they will never cross each other. That's because there are no magnetic charges. We know that there are electric charges, but the magnetic poles, they always come as dipoles, north and south poles. You can never reach only a north pole or only a south pole by dividing a magnet. If you have a magnet, if you divide it, the Neve divided parts also will have north and south. And you can go this indefinitely until you have, let's say, an atom. But even an atom, if it is a source of a magnetic field, how can an atom can be a source of a magnetic field? Do we have any part of an atom which is in motion? Electrons, yes. Electrons are circulating. Well, in classical picture, electrons are circulating. So the smallest unit for magnetic fields can be atoms, but these atoms should have electrons circulating in one plane. Some atoms have electrons circulating in randomly. It will not produce a net magnetic field. But if you have an electron which circulates in a one plane and in a regular fashion, this is the source of a smallest magnetic field. And even for that, the magnetic field it will be a circle, will be loops. Okay, I will show this when I define the magnetic dipole moment. What the magnetic dipole moment is, you will see what this definition means. All right, so before I delve into the concept of sources of magnetic fields, I will define what the force on a current carrying wire, if you put this current carrying wire inside the region of space where there is a non-zero magnetic field. Suppose you have this part of the region in space, we have a magnetic field. You see these are cross signs. What does this cross signs mean? The magnetic field is into the page. If you see dot like this, the magnetic field is out of the page, because we always need a third dimension to define the magnetic fields. You cannot only have everything in 2 dimensions. This is not possible for magnetic fields. This is possible for electric fields, but not possible for magnetic fields, because magnetic fields always require 3 vectors which are perpendicular to each other. So if you put a wire which has some current, constant current flowing through the wire, and put into a region of space where there is some magnetic field, then this wire will have a force on it. And this force is because every charged particle which is in motion are affected by this magnetic field, and there will be forces, magnetic forces on each charge. So as the total effect of this, you have a wire put into a magnetic field. It will be pulled in some directions which is perpendicular to the magnetic field, right? And also which is perpendicular to the direction of the current. If you put a wire which is parallel to the magnetic field, this wire will not experience a force, because B and the current, or the direction of the velocities of charges, is parallel. But 2 vectors, if two vectors are parallel, their cross product is 0. V cross P, if they are parallel or anti-parallel, it is 0, because V cross P depends on the sign of the angle between them. And if there is 0 angle between them, sine 0 is 0. Or if they are anti-parallel, the sine of 180 degrees is again 0. So they must have some angle other than 90 degrees, other than 180 degrees or 0 degrees to have a non-zero force on it. So the expression for this can be derived as the current that flows through this wire times this S vector. S vector is the displacement of this wire from one end to the other end. That's it. It's the length vector from one end to the other end, and it must be in the direction of the current. If the current flows in this direction, the S vector is the same direction with that. So it is nothing but S cross B, this magnetic field. So there is two vectors cross product, and so that means the magnetic force must be perpendicular to these two vectors. Whether they have a different angle, different than 90 degrees or not, the force vector will always be perpendicular to S and the magnetic field. All right, so imagine we have a wire which is in irregular shape. What to do then? Well, if it's a just straight wire, then it's easy. The straight wire has just a length as the magnitude of this S vector, and you can easily find the force. But if you have a irregular shape, then you can imagine this wire as the sum of small ds displacement vectors, and you find the force on each ds vectors and then add them all. So for only one ds, you can define df, the infinitesimal small magnetic force on it, and express the force in terms of ds. Of course, ds itself is a displacement vector, and it's in the direction of current. And ds cross p is just together with I, is the infinitesimal force on this wire, but only for a small portion. So to find the total force on this wire, you have to take the integral. But if you have a constant current, the current does not change at any part, in any portion of the wire, if it is constant, then in fact, without taking the integral, you can find this force. How do you find this force? Because if you add these ds vectors from point A to B, the result is just a straight displacement vector from point A to point B. That's it. If you can find this straight vector, then that's it. And you just multiply this S vector by magnetic field. As long as the magnetic field is uniform, the magnetic field must be uniform to do that. If it is not uniform, then you cannot do. So as you see here, to find the force, you take the integral. And as I said, if the magnetic field vector does not change at any portion of this wire, if it is uniform, then the integral only applies to ds. But sum of ds is nothing but, as I said, is the displacement vector starting from point A to point B. It's this vector, the black vector. Okay. So the result is I times S cross P. Well, in that case, remember, be careful. This S vector is not the total length of this irregular shaped wire. It's just the distance between the endpoints. That's it, not its total length. Okay? Because it's defined by the endpoints only. Just think in terms of vectors. You add vectors one by one from tip to tail, tip to tail. So you see these vectors as these small red lines. If you add them all, what you have this vector. We have to add these ds's as vector, not as length. This is the formula. if the formula says don't worry about the direction, you just add the total length, then it's okay. It's something else, the result, but you have to add them as vectors. Okay. Well, the next question is, what if you put a loop into the field? Should you have a force on the loop? It's a closed loop. 0, because if you start from one point, any point, and the current goes and comes to the same point again, so the displacement vector is 0. Just like in mechanics, you start from anywhere in space, you go around, wander around, and come to the same point again. What is your displacement? 0. So there is no net force on the loop, which is put inside a constant magnetic field. That means the magnetic field must be uniform. If the magnetic field is not uniform, this is not true. Just like the case of a dipole, remember? A dipole, one plus charge and one minus charge put into an electric field which is constant, will not have an external force, because the plus charge will toward one direction force, the minus charge will have the same magnitude of force but in the opposite direction. So in total, the dipole, which is put into an electric field which is uniform, will not experience a net force. Just like this, if you put a loop current inside a magnetic field which is uniform, there will be no force. But if the magnetic field is not uniform, then you will have a force, not net force. On the right, we will see these kinds of examples. This is only true as long as you have a uniform magnetic field. All right, so let's now think on a special example. Oops. You have this semicircular loop, current loop. Goes like this. And this upper part is just a semicircle, and this part is a straight wire, a straight current. But you have a constant current flowing through, and the magnetic field pointing the y direction, and this is x direction. The magnetic field is uniform. We will find the forces on the curved section and on the straight line section of this loop. The curved section is a semicircle, but you can immediately say that these two forces, total of these two forces on the curved section and the straight line must be 0, because it's a closed loop, right? It's a closed loop. You will see by calculating it. Let's start with, and first divide this loop into straight part and the curved part. And let's call the force on the straight part as F1 and the force on the curved part as F2. And let's express the magnetic field explicitly. It's just B times J, because it's toward the positive y-axis, and B is constant. This B is constant. And the force 1, which is on the straight portion, is just I times S cross B. And S, if it has a radius r, S starts at minus r in the negative x-axis and ends at the plus r in the positive x-axis direction. So it's easy that to express this S vector as 2r times I, right? Because it starts from at here and ends in here. So this is a vector, and it's pointing toward the positive x-axis, so must have positive I as the unit vector in the x direction, and its total length is 2r, just twice the radius. And this will be cross product by B, and B is in the direction of J, so I cross J is K. K is out of the page, right? Out of the page, Z, just the direction. So 2 times I R B. I is the current, R is the radius of this semicircle, B is the strength of the magnetic field. This is F1. And what about F2? How do you calculate F2? If you apply this rule of infinitesimally adding the small portion of this current, tip to tail, and express df and take the integral. Let's do that just to show. Well, you don't have to do that because just you know this starting point and you know the ending point. Just S is the inverse of this straight wire, and you can find the result. But let's try to do it explicitly by taking an integral. So what is ds? Okay, let's do some geometry. And let's take this ds, okay? This ds, and the starting point of this ds is shown by this radius vector. And let's take this radius vector having an angle theta with the x-axis, okay? Because we always measure the angles from the x-axis. And with this, ds is a vector which is perpendicular to this radius vector. So with this geometry, you can express this ds vector in both x and y components, right? And after all, what is the strength or length of this ds? If you have an arc, infinitesimally small arc of a semicircle. This is nothing but r times d theta, right? A portion of circle which has a theta angle d theta to the center has the length, total length, this angle times the radius. That's something we know from geometry, and you should also know. In Turkish, bir çemberde herhangi bir açının gördüğü yayın toplam uzunluğu nedir? Yarıçap çarpı o açıdır, değil mi? Onu biliyorsunuz. Değil mi? So, if this angle is very small, and then just multiply r by d theta, because we are talking about the infinitesimal lengths. So, but I have to write down this as a vector. ds is a vector, so I have to write down its x component and then y component separately. So let's analyze this ds vector in the yx coordinate system. So if this angle is theta, then this ds makes an angle with the y-axis the same angle, d theta. Just by geometry, again, you can check it. And this is the y component. And you can write down ds as a vector dsxi and plus dsyj. And if this length of the vector is ds, then the dxx, I made a mistake in here. This should be dsy and this should be dsx, okay? Sorry, let's correct this. This is x. And this is y. Alright, so dsx is pointing the negative x-axis, so it must be negative. ds times minus sine theta, right? It's pointing, because we're measuring the angle from here. And as the angle grows, the x component will grow in strength, but it will be decreasing in the sign signature. So, and similarly, dsy is just ds times cosine theta j, and we know what ds is. It's just r times d theta, and put everything on this formula to find df2, and I explicitly write down this ds vector, right? The strength is r d theta, and these are the components in x and y, and we have the constant magnetic field Bj. So if you do this cross product, you know that j cross j is 0. The y component of ds does not contribute to the force. Only the x component will contribute, and if you do this, I cross j is k, and we have a minus sign. This is the expression I times b times r sine theta d theta for the infinitesimal force, okay? I have to take the integral because the angle theta starts from 0 to, what's the limit of the integration? 0 to pi. 0 to pi. Alright, so I will take the integral from 0 to pi, and this is easy. You will find 2 times minus 2 times I times b times r. You see, the result is just equal in magnitude to f1, but it's opposite in direction. So if you add them, these two vectors, f1 and f2, you will find the total force on this semicircular current loop as 0, but we have just verified this, right, by explicitly calculating the forces on the straight portion and the curved portion. Yeah.
So we have the semicircular has force, right? Where it should be centered, this force?
The force acting on every portion of the wire. But if you sum all the forces, then it's 0. It acts at every point on the wire, because at every point of the wire carries a current, or at every point there are charges in motion. There is no one specific point that force acting on that point, nothing like this. On every portion will experience the force. So the net force is 0. Alright, so the next is, well, the force might be 0 on a loop which is put into a constant magnetic field, but let's think about this example. So we have a rectangular loop, and again, which is put into a region of space where there is a constant magnetic field toward right, and this rectangular loop has a current which flows in the counterclockwise direction, right? And it's a constant current. And we will find again the force on this loop, but we don't need to do that. The force is 0 because it's a loop. If there is a force on, let's say, let's first of all label all the sections of this rectangle. This 1, the top, 2, this portion is 3, and this portion is 4, and this side has length A, and this side has length B, and it's a rectangle. Think about this. If there is a force on, let's say, this portion 1, then the force on portion 3 must be just opposite, because the currents are flowing in the opposite directions. This similar thing applies to the portion 2 and 4. If there is any force on portion 2, then the same force but the opposite direction must be on the portion 4. So the total force is 0, obviously. But what about the torque? Torque is the capability of a force rotating an object, right? If you put this rectangular wire into this magnetic field, well, it will not go anywhere because there is no force on it, up and down or sideways, but it may rotate, right? Well, so let's think about this torque, and before that, of course, I have to find the forces on each section so that I can calculate the torque. But you can easily see that since the portion 1 and the portion 3 are parallel and anti-parallel to the magnetic field, these portions will not experience any force. The force on 1 is 0 and the force on 3 is 0, because the magnetic field is parallel to the current. But the forces on 2 and 4 is not non-zero, because the current and the magnetic field are perpendicular to each other. So, in fact, if you look at this loop, rectangle, let's say from top, right, from this side, you will see this picture. This is the side B, and the force on the second portion is on this picture, I cross B, well, it is into the page or out of the page? For this one, is into the page or out of the page? Out of the page, right? But since this picture is just from the side view, the force 2 will be upward, okay? And since the currents are opposite in direction for 4, so the force on the portion 4 will be down, because the currents are in the opposite directions. But the magnitude is the same. So as you see, with this picture, then these two forces will try to rotate the loop, right? If you look at this from this direction, in the clockwise direction. They will contribute to the rotation of the loop in the same direction. F2 and F4 will try to rotate in the same direction. So there will be net torque on the loop. And let's calculate this torque. So 1 and 3 is 0 because S and minus S parallel to the field B. And F2 and F4 in magnitude are equal to each other, but their directions are opposite. But you can immediately write down these magnitudes, I times A, the total length of the wire, times the B. That's it, because I cross S cross B is just this. S is the length of the wire. In that case, for 2 and 4, it is just A, and the same current flows, but their directions are opposite. Never mind, because they will rotate in the same direction, right? So what about the torque applied by, let's, F2? The torque, by the way, the loop will rotate through an axis which passes through just the midpoints of the short sides, B, right? And this is denoted by here, O. And F2 has a length to the center of rotation axis. It's just B over 2, and it's the same for F4. So if you multiply some force with a perpendicular distance to the rotation axis, then this is the torque, right? This is something you know from mechanics. So they will both contribute the same torque, and F2 times B over 2 plus F4 times B over 2 is the total torque, which is given by these two forces. And if you add them and find the result as the current, I, times the short side times the longer side, A times B, times the magnetic field B, strength of the magnetic. This is the torque, okay? So what you see in here, in fact, what is A times B? Small a, small b. It's the area of the loop, right? The torque depends on the area of the loop. And this is not unique to the regular shape loops. This is also true for irregular shape. You may have a very irregular shape, but it's a loop. Then the area covered by this loop times the current that flows through this loop times the magnetic field is the torque. This is true. This is a general formula. You may have any shape of the loop, whatever the area which is covered by this loop times the current times the magnetic field is the torque on that loop. All right. So this is a general expression, I times A times B. A is the area. At any position, position which is not this side B parallel to the magnetic field, you can again find the torque on the loop by this orientation. Well, this direction of the current, first of all, determines the area vector of this loop. What is the area vector? If some wire encloses an area, a plane area, the area vector is always perpendicular to this plane. Okay? It is perpendicular to this plane. You see from the side view, it is nothing but this vector. And its direction is determined by again, this right-hand rule, if your forefinger is in the direction of the current, then in this orientation, the area vector is out of the page. And here, it's perpendicular to the plane of the loop everywhere, and it is out of the page. So you can find at any position of any orientation of this loop, you can find the torque just by taking this cross product. Okay, this is the again formula, and in fact it is derived from what I have done before. It is just I, the current that flows through this loop, times its area vector. Area vector has the strength, the area of the loop, and the direction is determined by the right-hand rule. Cross product by the magnetic field. And this is the complete expression for the torque. And in fact, this cross product has the magnitude determined by the angle between these two vectors, area vector and the magnetic field. And in this position, the area vector and the magnetic field has 90 degrees. Sine 90 degrees is just 1. But you may have an angle which is other than the 90 degrees, a theta. In that case, the torque is I times area times B times sine of the theta. And theta is the angle between the area vector and the magnetic field. I will finish this by defining this spatial quantity, which is I, the current, times the area vector. This is called magnetic dipole moment of this loop. If you have a loop which flows a current, and this loop covers a region of space which has area A, I times A is just the magnetic dipole moment of that loop. Okay?
How can we know the direction of the area?
Just from the direction of the current. As I said, just put your forefingers in the direction of the current, because it's going like this. Your thumb. If it were flowing in the other direction, then you will do this. So the thumb is, in that case, will be into the page. But with this direction of current, it's out of the page. So we call this spatial product, I times A, as mu. It's a Greek letter. And it is magnetic dipole moment of the loop. Okay? Just like electric dipole moment vector. What was the electric dipole moment? Dipole moment for electric charges? Remember? Sorry? Electric dipole. What is electric dipole? Where's mine? What is electric dipole? If you have two charges, one plus, one minus, and if they keep the distance fixed in space, they define an electric dipole moment. They define a vector starting from minus charge toward the plus charge. This is a vector which we call P, and its strength is one of the charges, this is plus and this is minus, this is one of the charges times the distance between them. If the distance is d, and just like this, any closed current loops in magnetic fields defines magnetic dipole. This is electric dipole. If you put this electric dipole inside of electric field, like this, what happens?
Rotate.
It will rotate. Why? Because
Opposite force.
it will not direct to the left or up and down. It will not go anywhere because the total force is zero, right? But it will rotate. And the rotation defined by this torque is just P cross E. If the external field is E, just like this, we have just defined the torque on any current loop is mu cross B. You see the similarity? The field replaced by the magnetic field in this case, and the electric dipole is replaced by the magnetic dipole. Okay? And these are one of the most important things in your life, in your engineering life. What is electric dipole and what is magnetic dipole? You will all, in your life careers, will be dealing with these two units. This is very important for electrical engineers. Okay? They are the basic of electromagnetism. They are the basic of antennas. They are the basic of all electromechanical devices. Right? So you have to learn these. So let me give a break in here, and we will continue with another example.
Hocam bir önceki örnekte yarım dönme hareketi yapar mı?
Nasıl?
Bir önceki slaytta yarım loop var. Onda hani
Ha, yarım loop'ta olmaz. Yani yarım loop diye bir şey yok. Eğer current şey yapmıyorsa, kapanmıyorsa olmaz. Ama şöyle bir şey olabilir. Çoğunlukla
demin net kuvveti 0 bulduk yani.
Çoğunlukla şöyle şeyler göreceksin. Buradan giriyor, buradan çıkıyor. Yani tam kapanmıyor ama bu halde de yine şey, şurası bir manyetik dipol tamamlıyor ve dönme oluyor. Elektrik motorlarında temeli bu zaten. Elektrik motorunun bütün olduğu kanal.
Manyetik alanda.
Manyetik alan içerisinde bir loop koyacaksın. Bu da dönecek, tork döndürüyor. Elektrik motorun şeyi, temeli bu tork. Aslında yani elektrik motorun prensibini anlatırız.
Burada da hocam hiçbir şey var mı?
Ama şimdi şuraya bakarsan mesela bu dönecek. Bu tam ters yüz olduğu zaman diğer tarafa döndürmeye çalışacak.
Akım bu sefer yöndeş.
Böyle dönecek, sonra diğer tarafa dönecek. Böyle bir şey olacak. Yani onu tam yarım dönme yaptığı zaman bu akımın yönünü değiştirmen lazım. Akımın yönünü değiştirdiği zaman sürekli o zaman onun
Onu
dönecek.
nasıl yapıyorlar hocam?
Onu da şöyle yapıyorlar. Onu da şöyle yapıyorlar.
Hani çok aniden bir şekilde olması lazım ki onu dönme mekaniğinden yönlendirmesi.
Evet. Şöyle almaç dedikleri bir şey var. Tamam mı? Bu tam döndüğü zaman şu uçlar, şurada fırçalar var. Bu ikisi arasında boşluk var. Bu tam döndüğü zaman bu fırça buraya değiyor, bu fırça diğer tarafa değiyor. Daha doğrusu yarım döndüğü zaman akım yönü değişiyor. Şöyle olduğu zaman kuvvet, döndürücü kuvvet bir yönde. Başka bir tam onun yarım döndüğü zaman akımın yönü değiştiği zaman bu sefer yine tork aynı yönde devam ediyor. Akım yönü değiştirmiyor. Çünkü bunu akımın yönünü değiştirmeden bu tarafa gelirse bu akım şuradayken böyleyken buraya geldiğinde böyle olacak. Tersine olacak. Akımın yönünü değiştirmen lazım. Akımın yönünü de şu almaçla değiştiriyor. Şöyle bir şey. Bu döndükçe şunlar sabit. Bu tam yarım döndüğü zaman şu bu tarafa geliyor, bu yaya geliyor. Tamam, akımın yönünü değiştiriyor. Şey var, YouTube film var onunla alakalı. Burada hatta şeyi de koymuştum onu da. Burada da gösterebilirim sana.